you're going to be doing what's called a linear approximation for a function. It's also known as a tangent line approximation. So when you're asked to do a linear approximation at some point or a tangent line approximation at some point, you're going to follow this process. I am right here going to give you in the box the model, or the, for lack of a better term, it's not really a formula, but the formula for it. I highly suggest you follow this little disclaimer down here. Don't memorize it. If you understand how it works, this could be the easiest section you do for a while. If you're trying to memorize a model, you'll be successful on your homework today, but in the test next week, you're going to forget that. So understand, I'm going to create it so that you don't need to memorize. We memorize very few things in here, but here's one that needs memorization. What's the derivative of sine? Cosine. What's the derivative of tangent? Secant squared. Those little things need to be in your memory, but this you should just understand the process. So let's go like we usually do and make a fake function, and let's head it on like that. What we're going to do is make a tangent line at C, which you've done before. So we go to the point and we call it C, f of C, per usual. I'm going to draw the tangent line there. I'm going to nick it right here. And I'm going to tell you what you're going to use that red line for. You're going to use the equation for this line, whatever it might be, but it'll be y equals mx plus b-ish. You're going to use the equation to approximate what happens on the curve. Here's the deal. It's super accurate as long as you stay very, very close to that tangent point. You can see that right here on the red line, where I just put this dot on the red line and on the blue curve, they're almost on top of each other. So we'll be super close. But you can also see that over here on the red line, what's actually happening on the blue curve, I'll have a lot of error. I'll have a very large overestimate. So this process is great when you stay close to the point of tangency. So that's important. Then it's actually horrible. And we use another method that you don't learn until Calc 2. In Calc 2, we're able to deal with the curvature, and we actually, I'm going to give you a little history here just for a minute because it's important. I'm going to make the sine wave. All right, so here's my sine wave, right? You know around the unit circle the exact hits. Like you know at sine pi over 2 that's up here at 1. You know that, right? Agreed? What I'm going to teach you to do today is just draw a tangent line there, and you'll be super accurate in getting sine values really close to pi over 2. Historically, why was that significant? Because they didn't have calculators or computers that did it for them. You know what I mean? And they didn't know what sine of this was right here, so they'd approximate it. However, again, like I said, it's a really crappy approximation if I go far away. So what in Calc 2 you'll learn how to do, and it's really cool, is they don't use lines. This actually, the sine wave, if you were to take it and look at it just in pieces, like suppose you went from here to here, that actually kind of looks like a function. What kind of a function does that S-ish shape? What kind of polynomial does that? A cubic, yeah. And if I were to, okay, well, if I go this far, that's making that M shape. And that's very, very looking quartic-y, right? Quartic, I don't know if that's a word. But, and what we learn in Calc 2 is, don't use this line. This is pretty bad. I mean, it's really quite poor approximation. What we do is we fit a polynomial to the curve. And that, you might say, so what? That's how your calculators are programmed. When you type into your calculator, what's the sine of 17 degrees, your calculator has no clue. It hasn't been programmed with that value in some database, because otherwise when you hit 17.1, can your calculator also do that? Yes. How about 17.099? Can it take the sine of that? Yes. It doesn't have all the infinite amounts just sitting there in a database. What it does when you do sine of 17 degrees is it puts 17 into a polynomial that hugs the sine wave. And so it's super significant for programming. What you do today is going to seem a little silly because your functions are going to be simple. You're already going to know what they are. and we're going to use a tangent line that's not very accurate, but the thought process behind it is huge. Its actual execution is kind of, like I said, it's kind of a silly process because we're going to estimate what happens on the graph of f of x equals x squared at 8.1. But we have calculators, and I could just put that in. You know what I mean? But the process is important. You see why you're going to be like, oh, silly, why am I using this to approximate 8.1 squared when I can just go to my calculator and go 8.1 squared? That's not really the point. It's the process of it. When you get to the FRQs tomorrow, you're going to find that you don't know the function, so this process is unavoidable. So let's go take a look at the process. We already know how to find an equation for a tangent line. We take the point, which we're going to call CF of C generically. Maybe that's 0.3, 7. Those will be numbers. You're going to take the slope, and we always take the derivative to get the slope. So you're going to do f prime at that x value. So you're going to have two numbers sitting there. And you're going to do what we've always done. We've gone into point slope form. We're going to say y minus the y we know. Again, this will be a point like 2, 7, and you'll write y minus 7 is equal to the slope there, which will be our derivative. Maybe that was a half. And we'll plug in a number, times x minus the x we know. When you look up this section in our textbook, it's going to say y equals, they'll add this over. You're not going to memorize this. You're going to create it every time using point slope. Furthermore, in our book, they won't call it y. They'll call it t of x for tangent line approximation at x. Some texts call it L of x for the linear approximation at x. But really, all you're going to be doing is approximating y values using the tangent line. To get the tangent line, you're just going to use point slope. It simplifies it so much than memorizing the model. So let's go take a look at how your approximation, how good it is. So let's draw, suppose at C, your curve looked like this. And you did a tangent line to approximate what's going on the curve. Do you see how your tangent line is living below that? What's causing it to live below? You're going to have an underestimate when your function is what? Concave. Yeah, there it is. I heard it whispered. Concave up. So underestimate when f is concave up at that point. So let's say at C. I mean, it can be concave down over here. My linear approximation near this point, though, will be an underestimate. Likewise, if you're going to use it, let's go scroll down here. If you're concave down and you're doing a tangent line approximation right here, you can see that your line's approximation is going to be a little above what's actually happening on the curve. The College Board always asks this question. They'll say, is your estimate an over or an underestimate? If you just guess, it's 50-50. So you have to give the reason. You would say, I have an overestimate because the graph is what? Concave down at this point. So if that's C, yeah, concave down at that point. Otherwise, it's a guess. Now, to determine the concavity, if you can't see the graph, what do you have to do? Take a second derivative and plug it in. And if it's negative, so you might want to write, you know, this is where f double prime there is less than 0. This would be where f double prime there is greater than 0. Or if it's tabular, they'll tell you. I actually think I give you one on the test where you're reading stuff off of a table. But I tell you f double prime of 7 is -4. So you're to interpret that you're concave down there. All right, let's go do one. They're nice and easy, and I told you it's going to feel a little ridiculous. On this first one, I'm going to make the easiest function in the world, just so you get the process down. Y is equal to x squared. So equation to the tangent line right here at 2, 4. Here we go. We know how to do this. We've just never used the tangent line to approximate anything, but we've written them a lot. They always required a point. It'll be handed to you, for sure, the x coordinate. And if they don't give you y, just plug it in. You'll need the slope at that point. So you're going to need f prime at 2. The derivative, nice and easy, of x squared is 2x. Now there's some on your homework that are a little trickier. So you're going to have to know how to do that. And I'm going to pause for a second and throw a fake one out. One of the functions on your homework is like 1 plus tangent x to some power. It doesn't matter. That's not super hard to take the derivative of, but be careful. What rule will you use to take the derivative of? You're going to chain rule it. You're going to go 1/2, 1 plus tangent x to the negative 1/2, right? So it'd be 1 over 2 root, we got it, times what? The derivative of the guts, and what's the derivative of 1 plus tangent? Secant squared, and then you move along. So the derivatives aren't nearly as bad as your chapter 2 test. They're pretty straightforward. There won't be like a 4-layered chain rule or anything super. I don't even know that there's quotient rule or anything today. They're straightforward, just so you get the process down. So my derivative is twice x at 2, it's 4. And don't memorize the model. Don't think of anything to do with C's and f of C's. Just go to Algebra 1 from 7th or 8th grade and do point slope form. Y minus the y we know is equal to the slope there times x minus the x we know. The only difference is, for the tangent line approximation, you're now going to do two things. You're going to add the 4 over. Y is equal to 4 plus 4 times x minus 2. And you're going to rename y. You're going to call it a function, not f of x. F of x is already the original. What did I say we're going to call y? T of x or L of x. I'm going to stick with t. So my tangent line's equation is, and that's really what we just did. This is f of c plus f prime of c times x minus c. But we didn't memorize that, and don't. Do you see the power of being able to create it? You don't have to worry about clogging your brain with any sort of a formula. So this line right here has that equation. All the y values on the line can be found. That will approximate what's happening on f as long as you stay pretty close to 2. So we're going to go use our tangent line approximation to figure out what f of 2.2 is. You might say, well, that's stupid. I could do it on my calculator. You could. And so it does seem a little silly. You could just go, let's go do that. F of 2.2 actually is, somebody did it last hour, it's actually that. We're going to use our process to approximate that. All right? So do you think I'm going to get a number that is bigger or smaller than 4.82? Based on, it's going to, yeah, because that's concave up. So all I'm going to do is say this. F of 2.2 can be approximated by my tangent line at 2.2, which is, just go plug it in, 4 plus 4 times 2.2 minus 2. I'm on the line trying to approximate what's happening on the actual curve. I've got 4 plus 4 times 0.2. This is 0.8. I got 4.8. I got a super good approximation for what was happening. Why was it such a good approximation? I stay really close to the point. Exactly. The farther away I get, the bigger gap there is graphically, and the bigger distance there'll be between my actual value and my approximation. So again, it seems silly, but historically it's huge. Like otherwise you wouldn't be able to have a calculator where I did. Actually, when I was growing up, we didn't have the graphing calculators. For us to do like sine and E and ln, we had charts in the back of our book. And we'd have to go look. Like if we wanted to figure out what the sine of 17 degrees was, our calculators were not programmed to do that. So we'd have to go to the back of our book, go to 17, go to the sine column, and it would be rounded. But then what do you do when it says sine 17.0001? It was an issue. All right, so historically this was big. Right now it's kind of silly. One more, and then we're done. So I'm going to take a line. I'm going to make it tangent to this curve at 2. So I will have a point where it nicks the curve. I need to write that down. My point where I'm going to nick the curve is going to be at 2, comma, f of 2. F of 2 would just be 2 over 2, or 1. Then what I'm going to do is find the slope at that point, right? So my slope is going to equal f prime at 2. So I need to go take my derivative. I would do that off to the side. F of x is a power function to x to the negative first power. I am going to take its derivative. It's a nice easy one. It'll be negative 2 x to the negative 2, which will put it in the basement. I want to find f prime at 2. So nice, easy derivative. When I put the 2 in, I'll get a negative 2 over 4. Slope of negative 1/2. So that is nothing new. You've been making tangent lines all year. That should be a negative. I think I need to put a little gap there. So now I'm going to write my tangent line. I'm not going to memorize a model. I'm just going to say y minus the y I know is equal to the slope there times x minus the x I know. What two things am I going to do right now? I'm going to change the name. I'm going to move the negative 1 over and change the name. So I'm going to write y is equal to 1 minus 1/2 times x minus 2. And I am going to change this to either L of x or T of x, or I think on the word problems they actually have names, like you would call it R or radius, and be T, and we'll do some of that tomorrow. Today they're going to be all very generic. So it said I'm supposed to use this to approximate the value on the function at, did it say 1.9? Yes? All right, so my tangent line at 1.9 is going to be 1 minus 1/2. Do you like decimals or fractions? Don't mix the two. Either, if you don't have a calculator, you either should go all decimal or all calculator, or all fraction. Pick one. Go ahead, Freedom, pick. Do you want a fraction? So we'll do 1/2 times 1.9 minus 2 is negative 1/10. If he's going fractions, he's got 1 plus a 20th. What's 1/20th? So here, or he could just 1 plus 1/20th, right? Or 1 and 1/20. Could call it 21/20ths, I suppose. It's all good, right? If you went decimally, 1 minus 0.5 times negative 0.1, you would have 1 plus, we have to go back to elementary school. What's 0.5 times 0.1? You'd be, I know you feel like I'm insulting your intelligence, but I see a lot of decimal errors in this section. So what's 0.5 times 0.1? It's 0.05. Thank you. I get a lot of 0.5s on that one. 0.05. So here's my approximation. Who's got a calculator out? Somebody quick. Who's got one? No one? Come on. Oh, Lola, you do. Thank you. Lola, this is an approximation. So this is approximately f of 1.9. I want you to go get it exactly by just doing 2 divided by 1.9. What do you get? 1.052-ish is the exact. I have a slight underestimate. Why is it an underestimate? Concave up. Okay, how do you know it's concave up? Well, if you took the next derivative, right, it'd be 4 over x cubed, which is positive there. But I would actually challenge you to kind of thinking graphically. What does the graph of 2 over x look like? Who's its parent? 1 over x. It's just 1 over x stretched out. So this is graphically what you did. There's the graph of 2 over x. You went to the point 2, 1. Let's say it's right here. Made a tangent line. Used it to approximate what was happening just a little bit over at 1.9. And they're so close, but slightly under because the blue line's under. Right? Now, look at this. Had I used the tangent line to approximate what was happening at negative 2, holy cow, am I off, right? Because I went so far away. And why am I now an overestimate for over there? Because the graph is concave down over there. So it really matters where you are, but if the process makes sense to you, these are so easy. So you're going to go do this one on your own. Why don't you go do it right now? This should actually be near, not at. We're going to use it to approximate near 0. So go get your point, go get your slope, write your line, and then circle it. And I'm going to quit the video here. Those of you doing it at home, you should get a slope of 1/8. Oops, I wrote 1/2. You should get a slope of 1/8 on this one. And you should have an equation that is y minus 0.4 is equal to the slope there times x. And then you'd fix it. Those of you in class, they'll go create that.